This is a review of a Hardy-Weinberg equilibrium practice problem. Let's get started. So we've got a little bit of wordage here to do. So we've got the Grodsky-Smells syndrome, otherwise known as GSS. It's a recessive genetic disorder. That's important. That includes characteristics of tall stature and smelly fingers and toes. Okay. In the general population, this syndrome occurs in approximately 1 out of 175,000 live births. In a particular isolated population, however, the incidence of this syndrome is 1 in 200. And of course, in some biology classrooms, there is an incidence of 1 per classroom. Don't know which one that might be. Okay. So assume that both the isolated population and the general population are in this equilibrium. Okay, we're going to answer some questions. Now, what is this equilibrium? Well, it's an equilibrium with the idea that the allele frequencies are staying constant, and they're staying constant because of a couple of different parameters. Number one, there is no natural selection going on. We're dealing with a large population. There's no gene flow, okay, which means there's nobody coming in adding different alleles. There's no random mating, and there's no mutations. And those are the 5 parameters that allow us to have a constant number of allele frequencies. Now, we do use a couple of designations for the dominant and the recessive gene. So we use little p to equal the dominant allele. In this case, we'll make the dominant allele big G. And we use little p, Q, to equal the little g. Okay, so we're talking specifically about an allele from 2 chromosomes, the parental, the mother and the father. Okay, and we're talking about 2 different alleles in a gene pools. So anytime we're dealing with these values here, okay, the individual P or Q, we are talking about the what? The frequency, okay, of the what? Percentage or frequency of the total alleles in a gene pool, whether they are together, apart, what doesn't matter. So we're talking about the total number of, in this case, G's in a gene pool, and the total number of little g's in a gene pool. Of course, the gene pool is not going to be 4 alleles, but you can get the idea that these numbers or these letters are indicative of all the what? The alleles in a pool. So this is the total amount. It's important that you understand that. Now, when you consider the fact that there's only 2 alleles, so if you're going to mate, you're either going to give one or the other. So considering the fact that you have a mutually exclusive event, you are either going to have give a P or a what? Or a Q, or in this case, a big G or a little g. You're going to either have the dominant allele, which they told us the recessive disorder is for the recessive gene or the non-dominant one. So the P and Q, so either you're going to have big G or little g. There's nothing else. So in that case, you should know that the total choices of alleles is P plus Q equal 1, right? You think about it, if you flip a coin, and I keep going back to a coin, if you flip a coin, you either have heads or you have tails. So when you flip one coin, okay, what are the 2 choices? Heads or tails. When you make a zygote, okay, you either have the P that you're giving or the Q. Those are your 2 choices. From the gene pool, okay, what are your 2 different choices? P, or in this case, let's just do it, okay, which represents what? The dominant allele or little g. Those are your 2 choices. If those are the combined 2 choices, the total probability of you getting a G, big G, dominant, or little g is equal to 1. When you roll, in this case, flip a coin, what is the total outcome? Well, you're either going to roll a heads or a tails. There's no other choice. So the total outcome is going to equal 1. For instance, if I roll 100 times and I get 60 what? 60 heads over 100, that's 60 over 100, correct? That's, the total is 100, let's say flips of a coin, and 60 are heads. That's 0.6. Well, what's the other? The other has to be 0.4 for the tails. That's how that works. That's why we're adding these. And that's why P plus Q equals 1. You have what? Either you're going to roll a G. You have a two-sided coin that has a big G on one side and a little g on the other side. So when you flip it, you either get the big G, which is the P, or the little g, that's the Q. And what are the total possibilities? Either P or Q. So that's how that works. Now, that's when you're dealing with the total what? The total number of alleles. What if we are dealing with individuals? Well, if you're going to make individuals, party people, that must mean you're going to put together one individual mating another in the population to come together, and you're going to make a zygote. That zygote could be GG, that could be little g, and we can do all the phenotypes we want. But the point is, these are not going to be mutually exclusive events. These are going to be independent events. So I'm going to take the P plus the Q from the mom. It's either the mom's either going to be P or Q, or we should say the dominant allele or the recessive allele. And guess what? We're going to not add it, we're going to times it to the father, who can either be what? Little p, which represents the dominant gene, or the Q. This is not a mutually exclusive event. These are independent events, right? The formation of a zygote is an independent event, right? You can have, once you make a son from two parents, mom and dad, okay, you can still make more sons. Just when you roll a die that has 6 sides, you either have a 1, a 2, a 3, a 4, a 5, or 6. But that's a mutually exclusive event. An independent event, you can keep rolling the dice as many times as you want, and you can have what? 6 come up 3 times in a row. In this case, having 3 sons instead of daughters. Okay, so it's important to realize you're dealing with the multiplication rule. And when you do that, party people, you're dealing with a quadratic formula. And that's what occurs here. And I love it. I love seeing the math come out. So you do your FOIL first, you get P squared. Outside is PQ. Inside is PQ as well, so you get 2PQ. And of course you get the last when you do your FOIL. FOIL is a way for us to multiply this together. First, that's this, outer, inner, and now last is the Q times Q is Q squared. So my friends in chemistry, what just happened here? We just took one gamete and another gamete, either P or Q, that's what we're adding here, and another P or Q, and now we made individuals, and this is important, really important. You just made individuals. So when the question talks about individuals, and looky here, this part is looking for individuals. We are dealing with this equation. Okay? Look at letter A. Letter A states, please calculate the frequency of the alleles that causes the syndrome in the general population and the frequency of the allele in the isolated population. So they want the allele that causes the syndrome. Well, in the reading, they said it was a recessive disorder. So my friends in chemistry, or my friends in biology, I just messed up. Darn it. Okay? It's this little g here. So we want the total allele of G. Now, one important point while you're doing these problems, and let's get stuff out of the way, you really need to work from a phenotype that always gives you the genotype, right? I could be dominant, okay, big G, and I could be big G, little g. These both, because of the dominance of the G, will not show the syndrome. Now you should know that this guy is the carrier because it has the recessive allele, even though you're not going to express the disorder. But if you're expressing the disorder, you're one of the afflicted, you're going to be homozygous recessive, okay? And that is where we start from. You can't start from this phenotype of non-expressed of the syndrome because you can be of both. But knowing it's a recessive disorder, I can start from that point. Now, what point am I starting with? Well, if I go back into the problem, they said the number of people that are afflicted or have the syndrome is 1 out of 175,000. So I'm going to put, I know that this is 1 out of 175,000. Now, if you want to put the math in, we do. Take my calculator out, and so 1 divided by 175,000. And what I get is a very small number, obviously. And we get 0.5 zeros, 2, 3, 4, 5, and 57. Okay? So that is a small number. It's a small frequency. Okay? Now, what does it represent? It represents the what? The GG. They're looking for an A, the frequency of the allele G. Wait a minute, these are 2 Gs. These are individuals. The people that are afflicted are individuals. So I'm not talking about Q, I'm talking about what? Q squared. This value, okay, is equal to Q squared. That's important because they gave me the frequency, 1 in 175, and I found the number, the decimal, but it's the same thing. They gave me the frequency of the individuals that are afflicted. Knowing it is recessive, they gave me this individual. I have to start with the recessive because it gives me here. If I started with these values, I don't know if I'm dealing with one of these. Both of these types of individuals show no recessive disorder, so I can't start there. So my starting point is Q squared, so I start with the people that are afflicted because I knew it was homozygous recessive. So let's go find our Q because the question in A is looking for the frequency of the alleles, not the frequency of the people. So what I'm going to do is I'm going to find the square root of that number. So square root of Q squared is Q, and of course the square root, not of course because obviously you don't know this one. Let's put this number again, a 5 zeros and a 5 7. So I'm going to put this in my calculator. So 0.00000, so I have 500 and 5 7, and I'm going to take the square root of that. And just hold my horses here. I have make sure I have this right. And I get 0.0024. So what does this tell me? The Q is equal to 0.0024. That's my Q. That's my frequency of the recessive what? Allele in my entire population. Now that's of the general population. So I just did it, and let's make some room here. I just did it for the big population. Let's do it again for the smaller population. The smaller population is 1 out of 200. So I'm just going to write to it Q squared is equal to 1 divided by 200. These are people, okay? They're afflicted. It's individuals. This is the individual formula. So 1 divided by 200 gives me 0.005. Okay? But I want Q, so I square root it to equal my Q, because I want the number of alleles, not the people. So I'm going to square root my answer, and I get 0.07 is my Q. I'm just going to label this as the smaller population, Q of the small, and then the Q, well, and this is the Q of the large, and that's equal to 0.0024. So I've got the Q of the large, Q of the small. Okay, as you can see, in the smaller population, the frequency, which is about 7%, okay, the frequency of the recessive allele is much higher, whereas the frequency in the large population is smaller. Okay, that's A. Now B says, calculate the frequency of the individual. They're carriers. Now the carriers are the people that are homozygous. So that's my 2PQ. They said individuals, or how many animals. We're not dealing with total, so we have to use this formula, which by the way is given to you in your reference table. 2PQ, that's all I need. But wait a minute, I need my P. Well, that's easy. Let's make this very simple. The Q of my small population is equal to what? Let's find that. 0.07. Can anyone get me the P of my small population? Well, that's easy. What is that? 1 minus, right? Did we forget P plus Q equals 1? So if I know my Q is 0.07, my P of the small population is going to be what? 0.93. 1 minus this is 0.93. Let's change inks. The Q of the large population is what? 0.0024. What's the P of my large population? Well, 1 minus that is going to be what? And that will be, if you do 1 minus this, 0.9976. We're almost done. All we have to do now is put in the 2PQ. So for the red, which we make for the small, 2 times P, 0.93, times Q, 0.07. Let's go find that value. 2 times 0.93 times 0.07, and I get a value that is 0.13, which is the same as 13%. 13% of all the individuals in the small populations are carriers. Let's do the large. 2 times what? P times Q. The P is 0.9976 times 0.0024. That's the Q. And let's go find that value in our handy dandy calculator. 2 times 0.9976 times 0.0024. And what do I get here? I get 0.0048, which is the same thing as 0.48% of all the people have the phenotype G little g, right? That's what this means. G little g, which are your carriers. I could say in a problem, what's the frequency of the individuals that are homozygous dominant? GG, you'd be doing P squared. If I said how many individuals were homozygous recessive, that'd be Q squared. So notice something. The smaller population has a greater percentage of the P. The bigger percentage, the smaller population has a greater percentage of people that are carriers, whereas the bigger population has a smaller percentage. Why does the smaller population, who probably came from a bigger population, have a different frequency? What happened? Well, if I was to ask you, you'd probably say, well, which 5 postulates did we talk about could have changed? With a smaller population, think about what could have occurred to make the frequency change so drastically. And I won't give the answer, but it's important that you should know a smaller population will change that frequency. This is not natural selection, but that's why one of the parameters of Hardy-Weinberg is you keep the population large. Hope that helped.